Chem Crew! Sorry for the cringy intro, but everybody's got to have a catchphrase. Welcome to the first video in a series where I walk through introductory chemistry topics. I'm going to make this as fun and clear as possible, especially as we get into more complex ideas, so please don't be frightened by the idea of chemistry as this big mathy subject. It's really not, and I promise it's super interesting concepts, and it should all click by the time I've finished explaining. I obviously love chemistry and I absolutely love answering questions, so drop any chemistry questions in the comments and I'll answer them in the next video. Without further ado, welcome to Your Element. Let's get into chemistry. Today we're going to be talking about matter and pure substances versus mixtures. So what is matter? This might be a question that you've talked about with friends and family or that you already know the answer to, but the exact definition is pretty precise, so let's just get into it. Matter is anything with mass that takes up space. So this could be water, this could be your water bottle, this could be your computer, this could be me, this could be you. We are all matter. And so matter is anything. It's defined as anything with mass that takes up space. So in case you guys are like, well, okay, so what's not matter? It kind of sounds like everything is matter. That's actually a great question. So things that aren't matter are light. So light does not have mass. Heat, sound, those are not matter. Even though they're real things that you can think about that are not even abstract concepts or ideas, they are real things that you can physically see and feel. They are not matter. So it is just important to be careful about the definition that we use for matter. So matter is a cup, matter is me, matter is you, matter is slime, matter is oobleck, matter is rain. But it is not things, again, like light or heat or sound. So now let's get into the three types of matter that are most commonly talked about in chemistry. We're going to be talking about solids, liquids, and gases. It is important to note that there are also other types of matter like plasma, but we don't really need to be talking about that, so for now we're just going to focus on these three. So solids, liquids, and gases differ by a few things. I'm sure that in your guys' day-to-day life, you encounter all of these things. You know, when you get out of bed, your bed is a solid. When you get up and have your morning milk or water or coffee, that is a liquid. And say that night for dinner, you're cooking pasta and you put the water in, you get it on heat, it starts to boil, and you take off the top, and all of a sudden all the steam escapes into your face, and you're like, all of that steam is escaping is a gas. And when you walk outside and you breathe, there's carbon dioxide and there's air, and that is gas as well. So these are actually really, really, really common. We just don't often stop to think about what makes each of them a distinct state. So a solid is defined by the fact that all of the particles are super tightly held together on an atomic level. So when you get out of bed and brush your teeth, your toothbrush that you're holding, if you could take a microscope and go infinitesimally into the inner workings of your toothbrush, you would see all of these super duper duper tightly packed together atoms and molecules, which is what makes it a solid. A solid will always have a fixed shape, so you can't change it. That toothbrush, sure, you could break it, but if you breathe on that toothbrush or blow on it super hard, it's not just gonna all of a sudden change shape. It has a fixed shape and a fixed volume. Moving along to liquids have a fixed volume, but they don't have a fixed shape. If you knock over your glass of water and it goes flying, that water, that can be everywhere. Those droplets are gonna be soaking through the rug, they're gonna be on your shirt, they're gonna be on the table. It can go everywhere. The particles are much more loosely held together. As you can see, they're not as tightly packed as they are in a solid, where all of the atoms are individually packed together in a nice grid. In a liquid, they're just kind of more spread apart. Now moving on to gases. Gases are the most spread out. They have no fixed volume and no fixed shape. They are just free to go roam on their own. So when you are Actually, I think boiling water is a pretty good example. You get out the pot, that pot has a bunch of tightly packed together particles with a fixed shape and a definite volume. Then you pour some water into the pot, it still has a definite volume. There's an amount of water that you did put in the pot, and that's not going to change, but that shape can change as the water sloshes around and goes wherever. And then as you put the water on to boil and you let it heat up, eventually some of the particles will start evaporating and turning into gas, which can go anywhere. These particles are not bound by the shape or volume of the container that they sit in. These particles have enough energy to go wherever they please. So a big point about solids, liquids, and gases is that it is dependent on energy levels. So solids have the lowest energy. These particles are fixed in this formation and they do not have the energy to move. In a liquid, they are more spread about and the particles are moving with a little bit more kinetic energy. They're all moving around a little bit faster. In a gas, they have the most kinetic energy. They have so much energy that they're like, I'm not bound to the rest of you all. I can just leave right now. it could just go, fly away. That one particle could leave. And that's why when you start to boil water and it starts to just evaporate just a little bit, but it's not quite boiling yet, that's because not every particle in the liquid has enough energy, but just some of it, just a few particles get enough energy where they're like, you know what, actually, I can go away. And so then some of them turn into a gas where they move far away with more energy and can just leave. So that's sort of the transition between a liquid and a gas. And that should make sense along with what you're doing as well, right? Because you put your water in and it's, room temperature water. And as you heat it up, as you are literally giving those particles in that liquid more and more energy, it boils. Those particles get enough energy to the point where they can spread out. So what you are actually doing in transitioning between a liquid and a gas is giving the particles in a liquid, which are already sort of spread about, so much energy that some of them turn into gas and then will evaporate and go on their own. And on the reverse, on the contrary, when you freeze things, you are taking a liquid where the particles are relatively tightly held together and you are turning it into a solid. You are decreasing the temperature. You are taking their kinetic energy is leaving. You are getting rid of their energy. You're lowering it. So they are all coming together. They're moving not so fast anymore. Now they're just kind of all in a little jiggly solid going. Now we're going to move on to pure substances versus mixtures. So a pure substance is kind of exactly what you think it is. It is just a substance that only has one type of particle, which could be one atom. For example, it could be O2, oxygen. It could be one molecule, for example, water, as I've drawn here. And it is just like, it is sort of like a metaphor for that could say, if you go apple picking and get 10 Granny Smith apples and put them all in a bag, in that bag you have a pure substance. You have exactly one thing and it is a Granny Smith apple. And you have multiple copies of that single thing. So for example, in the water that you drink every day, this is what it looks like. Each of these H2O molecules looks like this. Now you might be sitting here thinking, but Adele, there's multiple atoms. There are, yes. Within each H2O molecule, it is 2 hydrogens and 1 oxygen. However, those are actually bonded together. We are looking at the unit. So these are bonded together as multiple atoms, but each unit of water, this is one molecule of water, is what we're referring to. So there are multiple molecules in here. There are multiple atoms in here, but there's one molecule, which is water. Now, a mixture, there are 2 types of mixtures. One is homogeneous or homogeneous, the pronunciations vary, and one is heterogeneous. So a homogeneous mixture, which we will start with, is one that appears to be completely uniform, but in reality it's not. So a homogeneous mixture kind of disguises itself as a pure substance. You could look at that and think, that's a pure substance. For instance, salt water is a homogeneous mixture, because you have put salt in water, but you've mixed it so vigorously that all the salt has dissolved into the water. But if someone gave you 2 cups, one filled with pure water, which as we discussed is a pure substance, and one filled with salt water, which as I just mentioned is a homogeneous substance, you would not be able to tell which is which, because the idea behind a homogeneous structure is that it looks exactly as a pure substance would. It looks like it's just one thing going on, but in reality, it's individual molecules that have been mixed together that are different. So for example, air is another homogeneous mixture. When you look at the air, you don't see anything. I mean, you would have no idea if that's a pure substance or not, but many people would guess that air is a pure substance, but it's actually not. It's filled with nitrogen, oxygen, and carbon dioxide. All 3 of them have been mixed together. It's also important to note that these are physically mixed together. There is no chemical bonding. The nitrogen is not bonded to the carbon dioxide, and none of them are bonded to the oxygen. There are just 3 living in harmony species that appear to be one when you look at them. So like salt water, which would have the water and the salt mixed together, but in reality, it's got 2 things in it, even though it only just looks like one. So that's a really important note. Because they are all physically mixed together, they're also separable. We will have an entire other video on methods of separation such as distillation or chromatography, but these are all separable. They're just kind of all in the same room together. Now we'll talk about a heterogeneous mixture. A heterogeneous mixture is one that does not appear uniform. You can literally see all the differences. It's not such a good disguise, good like sneaky spy as the other one is. So a homogeneous mixture kind of looks like a pure substance, but a heterogeneous mixture is just like, hey, look at me, I am not a pure substance. So for example, salad. If someone gives you a salad, you can see the lettuce, you can see the tomatoes, you can probably see the dressing dripping off of it. It doesn't look like one thing. You can tell that there's multiple. Or if you put oil and water in a jar, you can physically see the separation between the 2. Or if you go to the beach and you see the sand in the water, like they might be mixing, they might be in the same thing, but you can tell that they're different. So an example that combines the idea of homogeneous and heterogeneous mixtures is you going to the beach. So say this is you on your little way at the beach. And at the beach, we see the water and we see the sand. Inside the water is going to be a homogeneous mixture. So the water is actually water and salt, as we discussed before. But when you scoop up a scoopful of water, at the beach, you don't see the salt granules in it. You just see water. So it is a homogeneous mixture. But the water mixed with the sand that happens as you walk through it, when you kick sand up into the water and it's a little mixture, that is a heterogeneous mixture. You can see the two separate pieces. But it's important to note that both of these are mixtures. Even though the homogeneous mixture of the salt water doesn't look like two separate things, it is. And you could still separate them. For example, if you took up a bucket of the water here and brought it all the way home with you, and put it on a plate and let all the water evaporate, eventually you would be left with a plate of salt, of pure salt. So you would have then separated them. To sum this all up, heterogeneous and homogeneous mixtures are both mixtures that have different components that have been physically mixed together. So they both have multiple things that have been all put together. The difference is that in a homogeneous mixture, it appears to be a pure substance because they're so well mixed that you just can't really tell. Whereas in a heterogeneous mixture, they're not that well mixed and you can absolutely tell. So I don't know if you guys are really word people or not, but if you are, you might recognize that the word hetero means different and the word homo means same. So the idea is that homo, being same, is that it looks like it is all the same, whereas hetero, being different, looks like it is all different. But neither of them are pure. Both of them contain multiple components. So our last topic that we're going to cover today is going to be elements versus compounds. So I'm sure many of you guys are familiar with the periodic table of the elements, which lists out all of the elements based on chemical and physical properties. So an element includes N2O2 Au, which is gold. This is nitrogen gas, oxygen gas. There are many, many, many others, which I will not list. But if you look at the periodic table and pick anything on there, that is an element. I only bring up these examples because sometimes people can get confused by the fact that there are two oxygens. So this is going to be what these two oxygens together would look like. Don't worry about that structure. We will get into that at a later date. But I'm just trying to familiarize you guys with the fact that sometimes, even though it's an element, it can be what we call diatomic or have two of the same atom within the same thing. And that does not make it a compound. A compound refers to two different elements that are put together. So when atoms of different elements come together, it makes a compound. So I'll say that one more time. It has to be atoms of different elements. Atoms of the same element, like an oxygen and an oxygen, are going to make O2, which yes, has a subscript and yes, is more than one atom, but that is still an element because they are atoms of the same element. When atoms of a different element come together, such as in glucose, it makes something what we call a compound. So glucose has the formula C6H12O6, and it is called a compound because it is atoms of carbon, atoms of hydrogen, and atoms of oxygen, 6, 12, and then 6 of each respectively, that come together and bond to form glucose. Carbon dioxide is another compound because it is 2 oxygen atoms and 1 carbon. Or table salt, which you sprinkle all over your food. NaCl, that is also a compound because that is combining 2 different elements. So that is the brief introduction that we will have to element versus compound. Okay, so before we wrap up, we do have some practice problems. We're going to talk about it and we're going to explain the answers. So first off, we have matter or not. I will give you a little bit of time, but also feel free to pause the video if it is not enough time to pick your answer. So for matter number 1, we have a rock. 2, we have heat. 3, we have oxygen gas. 4, we've got light from a lamp. And 5 is sound waves. So please make your guesses. Do feel free to take as long as you need. All right, so we are going to go over them now. Here are our answers. First up, we have a rock. A rock is matter. Yes, a rock. What is the definition of matter? Yes, exactly. Matter has mass and takes up space. And a rock has mass and takes up space. Next, we have heat. We talked about this earlier. No, heat is not matter. Oxygen gas, this is kind of tricky. Yes, it is. Even though it is a gas and it is a little bit more abstract, you cannot hold, for example, oxygen gas. It is still matter because it still has mass and takes up space. Then we have light from a lamp. No, it is not. Light is not matter. We have sound waves. Similarly, sound, nope. Now on to the next section of questions. We have element, compound, or mixture. But for mixture, I'd like you to be even more specific of homogeneous or heterogeneous mixture. So these are your choices. For each one, please assign it one of these. So the first one is brass, which is an alloy, which basically means a combination of copper and zinc. Then we have CO2, sand and salt mixed dry as a mixture. Sucrose, oops, I kind of gave that one away. Sorry about that. Sucrose, which is a type of sugar, or milk. So please think on that. I'm going to move along, but please do pause the video. Yes, so brass is a mixture. It is a homogeneous mixture. It is homogeneous because you can't tell. When you look at brass, for example, a brass ring or brass coil or anything, it looks as though it is all one, while in reality it is a combination of copper and zinc. It is a physical mixture, not chemical. That is part of what the definition of alloy means. That may have been a bit confusing by this, but it is a physical mixture. Next, we have CO2. This is a compound. We talked about this earlier. CO2 is a chemical compound. It is a combination of two different atoms, different elements into one. So there's two different elements. It is carbon and it is oxygen, making it a compound. Now we have sand and salt mixed dry, which is a heterogeneous mixture. This is visibly different. I mean, it might be a little tricky if your sand and your salt look kind of similar, but if you actually think about it, you are mixing together sand and salt. They could look pretty different, and when they're mixed together, it is going to be a physical mixture of different things that visibly does not look as though it is all one. Next, we have sucrose, sugar. We did talk about a very similar thing earlier, which was glucose. It is a compound. It is a combination of different elements to make up the single compound of sucrose. And milk is a homogeneous mixture. Milk has many different things inside of it, but it is a mixture. They're all physically mixed together, but it looks as though it is one, unless you have spoiled milk, of course. Lastly, we have teach back questions. Teach back is my absolute favorite way to learn, so I strongly recommend doing this when you are studying for an exam or just want to deeply understand something, is teaching back. So teach back questions, the way that they'll operate is that I'm going to ask a question and then I encourage you to pause the video and teach it back as if we were just having a conversation and I had asked something because I didn't know and you were explaining it to me. This can also be helpful to go back at the end of a given unit or before an exam to prepare, and you can just teach this back to a friend, to a parent, to a stuffed animal, to a dog, anything. It is just helpful, in my opinion, because if you can truly explain it back, that means that you deeply understand it and you are prepared for questions. And I'm going to ask these questions, then you guys are going to pause the video and answer it back to me as though we're just having a conversation. So first of all, could you please explain to me the difference between a homogeneous mixture and a heterogeneous mixture? Like, what's the difference? Okay, I hope you guys did that. A homogeneous mixture is uniform throughout. It is mixed together. They are both physical mixtures. However, a homogeneous mixture looks as though it is one, like a pure substance, and a heterogeneous mixture looks as though it has been poorly mixed and it does not appear as one. You can see the different types. Next, can you tell me, why is air a homogeneous mixture, even though it kind of looks like a pure substance? I hope you've had a chance to answer that one. Air is a homogeneous because it is a combination of nitrogen, oxygen, and carbon dioxide, as the diagram on the last page showed. It does look like a pure substance simply because we can't see it. Next, this one is a trick question, hence the blue asterisk. But is tap water a pure substance or a mixture? And why? All right, tap water is actually a mixture. Pure water, as we discussed, I know this could be confusing because I did say that water was a pure substance, and it is. Water in a pure form is a pure substance. However, your tap water contains many minerals, many things that have come up in your drain and your pipe. It just has all these minerals in it, and therefore tap water is a mixture. Thank you guys so much for watching. I hope that you've learned a lot and that concepts that might have felt fuzzy before feel really clear now. Once again, I really love to answer guys' questions. That's exactly what I'm here for. So please ask anything or clarifications, even if you think it's a silly question, in the comments below. That was lesson 1 of your element. Goodbye, Chem Crew. I'll see you all next time.